Question 10, last question of the paper. You've gotten here. Well done, guys. Okay, last one's Euclidean. Question 10, in the diagram, PQRS is a cyclic quadrilateral. Okay, while we're doing that, I'm just going to highlight it with a color so we know. So PQRS is this bad boy here. Okay. And then we've got such that PQ equals PR. Okay, so that's PQ equals PR. So that's this over here. Those are equal. Okay, great. Now that we have that, the tangents to the circle through P and R meet QS produced at A. That's on the drawing. RS is produced to meet tangent AP at B. That's in the drawing. And then PS is produced to meet tangent AR at C. PR and QS intersect at M, all in the drawing. Okay. So, very important, guys. A lot of people skip this paragraph and then go straight to the question. Now, there was a piece of information here that was not represented in the drawing that we had to extract from the paragraph, and that was PQ equal to PR. If you didn't put it into your drawing, and if you skipped this whole paragraph, you would not have those two pieces of information, and you would have gotten stuck somewhere here. Okay, so please, guys, it's so important to please read your paragraph, and whatever is not in the drawing but is in your paragraph, please put it into your drawing. Vital, vital, vital. Okay, so first question, prove giving reasons that 10.1 S3 equals S4. Okay, so this angle and this angle are the same. Now, let's start off by letting something be x, because obviously we have a few things here. Well, let's also highlight some important facts. These are my tangents, and I'm going to highlight those in blue. Okay, I know that they are meeting at a point on the circle, and they're extending to the same point, which automatically tells me that I have AR and AP are equal. I haven't written this down, I'm just stating what I can see. Okay, then let's let something be x. I would let P4 equal x. Okay, sometimes you would have to look at it for a bit to see some matching angles to be able to choose what you would let be x, but because I've done these so many times, I can kind of see immediately that making P4x will actually fill in a lot of angles here in x. My first one would be tan chord theorem. So there is my triangle, there's my tangent. The angle that the tangent and the chord makes is equal to the opposite interior angle of the triangle, which in this case is R3. So I'm going to say that's equal to x. Okay, and because that's equal to x, Q1 and 2 is also equal to x because of angles opposite equal sides. Okay, after that, I can then state that S3 is going to equal x. Why is S3 going to equal x? Because of my cyclic quad and exterior angles. So the exterior angle of my cyclic quad is equal to the opposite interior angle. So basically all I've done here is I've already checked that S3 is equal to x. Now to let S4 equal x, or try and figure it out. And that one isn't so bad, because here, because they stated that this was a cyclic quad in the beginning, it means that S4 and R3 are equal because of angles in same segment. Everyone see my butterfly? Okay, so S4 and R3 are also equal to x. And voila, I have achieved the goal of proving S3 is equal to S4. Okay, so you can start off by saying 10.1, let P4 equal x, therefore R3 equals x, reason, tan chord theorem. Therefore, Q1 and 2 equals x, and that's because of angles op equal sides. Therefore, S3 equals x because of exterior angles of cyclic quad. Therefore, S4 equals xy, that was angles same segment. Therefore, S3 equals S4. Statement finished. Okay, fantastic. Then the next one, 10.2. Let's just also put a tick here because we managed to get that to equal X as well. 10.2, let's have a look. Is a cycle, so prove that SMRC is a cyclic quadrilateral. Let's use yellow. SMRC, so that's here. Proving that it's a cyclic quad. So there's three theorems that come into play there: angles in same segment, exterior angles of a cyclic quad, and then opposite interior angles are supplementary. Okay, so SMRC, what can we prove so far? Well, I know, let's fill in more x's, shall we? So I know that S1 will equal x. That's because of opposite, vertically opposites, so S4. And then I can also state that this is also going to equal x, so that's also x. Fantastic. I don't have the other line from C to M in order to use angles in same segment here, so that's not going to work. I can, however, use exterior angles. So if I can prove that R1 and 2 is also x, then I'm golden, because then I can use converse exterior angles of a cyclic quad. Opposite interior we can also use, but I don't feel like we have enough information there. So is there a way for me to work out R1 and 2 to equal x in this instance? Let's have a look. And yes, there is, because we can use tan chord theorem. So look, there's my tangent. There is my triangle. Okay, triangle, tangent. This angle, which is the angle made with the tangent and the chord, is equal to the opposite interior angle. So I can therefore say that that is equal to x, and there I have proven it. For this, to prove it's a cyclic quad, angle S1 is equal to angle R1 and 2, reason being converse exterior angles of a cyclic quad. Converse theorem because we are proving a cyclic quad by proving angles equal. Okay, so what did we do first? The first thing that we stated was S1 equals x. Reason, vert op. Okay, therefore R1 plus 2 is equal to x. Reason, or we can say R1 is equal to Q1 plus 2, which equals x. Reason, tan chord. Okay, so rather also stated here, S1 equals S4, which equals x. Okay, vertically ops. Therefore, S1 equals R1 plus 2. Therefore, SMRC is a cyclic quad. Reason, converse exterior angles of cyclic quad. Okay, a lot of people opt to use the X method by making something X because it's easier to see. Okay, but others don't. Others will just use the angles. Okay, it's all up to you and your comfort. 10.3, RP is a tangent to the circle passing through P, S, and A at P. So we need to prove that RP is a tangent to the circle. Okay, so let's use another color here. Let's use purple. So RP must now be my tangent to the circle passing through P, S, A, P, S, and A at P. Okay, so we want the tangent to be here, P, S, and A. So there's my circle. So my circle's doing that, basically. Okay, so that is within my circle. Okay, so is there a way for me to prove? So what I would gain to prove here is if I can prove that P2 is equal to A2, then I've proven that it's a tangent through converse tan chord theorem. Okay, another way, and that would be the only way here. So the goal here is to prove that P2 is equal to A2. See how I've mapped out what I need to do? Okay, so let's have a look. Okay, I see it. But I must admit, guys, I haven't seen such a hard Euclidean geometry question in a very long time. Okay, so hope you got your seatbelts on. This is going to blow your mind. Okay, so always use what you've proved before in order to answer your questions that follow. So the fact that we know S3 and S4 are equal is an important fact. Okay, so let's now, in order for me to get A2s and P2s, the only thing that I can see here is exterior angles of a triangle. So when I say that, S3, or let's say S4 first, do you agree that S4 will equal A2 plus P1? And that's because of exterior angles of a triangle. Okay, and the other one, so S4 is done. S3, okay, so let me just show you. There's the triangle that I just used, okay? And S4 is the exterior angle of these two. Okay, so triangle SAP, the exterior angle of that is S4, which is equal to A2 plus P1, okay? Then the other exterior triangle, so S3 now. So RSP is the triangle I am dealing with here. And this line is being extended. So the exterior angle is S3 would be equal to R2 plus P2. Okay. So S3 equals R2 plus P2. And that's also because of exterior angles of a triangle. And didn't we prove earlier that S3 and S4 are the exact same thing? Yes, we did. So therefore we can state, or let's also maybe put that in as a step, S4 equals S3 proven. Therefore, A2 plus P1 must equal R2 plus P2. Now, and this was the trick to bring P1 into it. P1 is also equal to R2. Why? Because of tan chord theorem, guys. Here's my tangent. There's my triangle. So this angle that PB makes with SP, that angle P1, is equal to the opposite interior angle, which is R2. Okay, so P1 equals R2. Why? Tan chord. Therefore, let's change everything into, that's just going to be A2 plus R2 equals R2 plus P2. Those are ending up to cancel. So therefore, what did we set out to do? Prove that A2 was equal to P2. And that's what we wanted, right? To use for the purple to prove our tan chord theorem, so we can use the converse theorem to prove that RP is exactly a tangent. So we have now proved that P2 is equal to A2. That's what we've done here. So therefore, RP is a tangent at P, reason, converse, tan chord. I'll be honest with you, I haven't seen a hard question like that in a while. And it was a bit of an ugly one for them to put last, but that's how it goes. Last questions are normally the harder ones. Okay, so I hope that makes sense. I hope you understood that. And yeah, I look forward to seeing you guys with the next paper. Great. Have a good one.